So we're going to take a look at a couple word problems, but before we do that, I want to sort of step back for a moment and compare this mean value theorem to another theorem that we talked about earlier in the year, the intermediate value theorem. These are both examples of what we call existence theorems. They guarantee, under certain requirements, that something happens with our function. Our intermediate value theorem was used to guarantee that our function would equal a specific y value. It was used to guarantee, wow, this is a mess. Let me try that again. It was used to guarantee that f of x equals some particular value. We now add to that list our mean value theorem, which is used to guarantee not that our original function equals a particular value, but that the derivative equals a particular value. If I want to try to guarantee my function equals some specific value, I'm going to use my intermediate value theorem back from Unit 1, Section 1.4. If I want to try to guarantee that my function, that the derivative of my function equals a particular value, that's where I'm going to use the mean value theorem. I also guess we can add to this list Rolle's theorem, trying to guarantee that somewhere the derivative equals 0. Although I'm not going to use Rolle's theorem too often, I think I'm just going to keep going back to mean value theorem because I find that a little bit easier. Let's take a look at the packet titled Mean Value Theorem Word Problems, Section 3.2. We're not going to take a look at every single one of these, but I do want to take a look at a few. Take a moment, read through the problem, please. Over the time interval between 0 and 2, what must the speed of the car have been at some point? Well, I know the speed, or the velocity, is the derivative of position. I have information about my position. I want to guarantee a particular derivative happens. So I want to use the mean value theorem. Is the position of the car continuous and differentiable? Yeah, sure it is, because it said that in the statement of the problem. I'm not asked to justify things. I think I can just go and start doing that calculation. Somewhere the derivative has got to equal the position at time 20 minus the position at time 0 over 20 minus 0. Let's see, this is 14 minus 0 over 20 minus 0. 14 over 20, or 7 over 10 miles per minute. I know that somewhere between time 0 and time 20, that car was going at a speed of 7/10 miles per minute. Now, I don't know about you, but that doesn't mean a whole lot to me. It would make more sense to me in terms of miles per hour. Just for fun, go convert that to miles per hour. 7/10 miles per minute is how many miles per hour? Well, I think all we have to do is multiply that by 60. I'm just going to do this on my calculator. I'm going to get 42 miles per hour. And the point is, I know nothing about the speed, the velocity at any of these times. But because of my mean value theorem, I know that somewhere between time 0 and time 20, that car was going 42 miles per hour. Letter B. How about you go do letter B? Give the answer in miles per minute, and then just for fun, let's convert it to miles per hour as well. What speed in miles per minute must that car have been going? S of 50 minus S of 30 over 50 minus 30. Okay, that's 31 minus 20 over 50 minus 30. That's 11 over 20, 11/20 miles per minute. And what's that in miles per hour? Again, just for fun. Multiply that by 60. I think that's going to give us about 33 miles per hour. Oops, you can't see that. Sorry about that. Part C. See what you can make of part C. What must happen within that interval? Well, I'm going to go and I'm going to do my s of 60 minus s of 30 over 60 minus 30. That's a 20 minus 20. Oh, okay. Sorry, once again, you still can't see that. Looks like my derivative is guaranteed to be 0. Well, if the speed is 0, that means the car must be stopped. I don't know when exactly, but I know that at some point between time 30 and time 60, that speed was 0, so that car was stopped. And I think this is kind of interesting. All we have are certain positions of the car, but we can use those positions to guarantee that at some point you're traveling at a certain speed. Turn the page. Actually, before you turn the page, I'm going to make the video pause if you need another moment to copy things down. And then turn the page. Take a moment and read problem number 2. So here I have velocities and accelerations. Is there a time when the velocity is -5? Well, I have my velocity over here. I have my velocity. I want to know if my velocity is -5. Does that mean use the intermediate value theorem or the mean value theorem? I think because I have the velocity and want to know about my velocity, I can try to just use my intermediate value theorem. Let's see. I've got a velocity of -20 there, a velocity of 10 there. Must the velocity be -5? Sure. So we need to try to write this out. Because v of t is continuous. Is v of t continuous? Yeah, they told us that it was a continuous and differentiable function. So I'm going to say because v of t is continuous on the closed interval between 0 and 60, and because the velocity at time 0 equals -20, and the velocity at time 60 equals 10, by the intermediate value theorem. My velocity must equal all values between -20 and 10. Specifically, there exists, I guess normally I'd use C, but I guess here they're just saying T, so I'll say that. A T such that V of T equals -5. And this language should look the same language that we were using back in Unit 1. Take a moment, get that copy down. Next one, letter B. For time 0 to 60, must there be a time when the acceleration is 0? Take a look at your acceleration line. Can I use the intermediate value theorem to prove that somewhere my acceleration is 0? I don't think I can. If I had a negative value somewhere, then I think I could, but as is, I can't use the intermediate value theorem on that. However, maybe I can use the mean value theorem. Hold on one second. Yeah, maybe I can use the mean value theorem, or even Rolle's theorem, to try to prove that somewhere the derivative of my velocity is going to have to equal 0. Can you see an interval where the slope is going to have to be 0? If we look at between 0 and 15, negative 30 minus negative 20 over 15 minus 0, I don't think that slope is going to be 0. If we look between 0 and 25, oh, wait a minute, I think that's going to work. Negative 20 minus negative 20 over 25 minus 0. We can use the mean value theorem on that smaller subinterval, 0 to 25. Here's how we'll write this out. First of all, v of t is continuous on the closed interval from 0 to 25, because I said it was in the original statement of the problem. V of t is also differentiable on that interval. I'm just going to focus on the open interval, but it's all good. Therefore, the mean value theorem applies. Which means that somewhere v prime of t, or a of t, has got to equal whatever v of 25 minus v of 0 over 25 minus 0 gives us. Well, that's negative 20 minus negative 20 over 25 minus 0. That's 0 over 25. I'm guaranteed that somewhere the derivative of velocity, the acceleration, is going to equal 0. If you need a moment to copy that down, I'll make the video pause. I think I don't want to bother with part C for right now. I think you can probably handle that. Maybe let's take a look at one more. Read problem number 3 for a moment. Okay, it took 20 seconds for the temperature to rise from 0 degrees Fahrenheit to 212 degrees Fahrenheit. Explain why somewhere the temperature was increasing at exactly 10.6 degrees Fahrenheit per second. Okay, that's kind of random. But here's the deal. I want to guarantee the temperature was rising at exactly this rate. This is the derivative of my position, of my temperature. I want to guarantee that somewhere the derivative of the temperature will equal this. I can use the mean value theorem to do this. First of all, because temperature, and why don't I start putting like some appropriate math notation here, we'll call the temperature T of T, is continuous and differentiable. How do I know that? Well, think about how like the temperature works of something. You can't like automatically jump from like a temperature of 200 degrees Fahrenheit down to 100 degrees Fahrenheit without going through all the temperatures in the middle. Similar with the derivative. There are no sharp, sudden changes. There are only gradual changes. Because the temperature is continuous and differentiable, by the mean value theorem, somewhere the derivative of the temperature has got to equal the temperature at time 20 minus the temperature at time 0 over 20 minus 0. Was the temperature at time 20 212 degrees Fahrenheit? Temperature at time 0? 0 degrees Fahrenheit. Maybe I don't need the units in the work, whatever. Over 20 minus 0. I'm going to get 212 over 20. Go to your calculator. I think that's going to give us 10.6 degrees Fahrenheit per second, the exact rate that I was trying to guarantee happened. That was fortunate, because if I was trying to guarantee that somewhere the temperature is changing at exactly 10.4 degrees Fahrenheit per second, I wouldn't be able to do it. There's only one particular rate of change of the temperature I can guarantee given the little bit of information I had here, and it happens to be 10.6 degrees Fahrenheit per second. What you really need to know leaving this is that if we want to guarantee a particular function value, f of x value occurs, we use the intermediate value theorem. If we want to guarantee a particular derivative occurs, we need to use the mean value theorem.